come back from when we did our functions and our rationals, and they happen with your rationals, because your denominator usually has a number that you can't use. It has some kind of restriction. Now, these direct substitutions have no restrictions. So therefore, we're able to directly substitute it in. An x value can have a limit. It's the y value of that function. If it's there, it is its limit. If it's not there, we can see if it approaches that one number from both sides. If it is, that's your point of discontinuity. You can come from both ends and remove that little point. In the first couple, all you had to do was substitute it in. There were no restrictions here. Even though this has a denominator, this guy has no restrictions. There's nothing that you can put in for x that will give you a 0 in your denominator. So are everybody okay with those? Just directly substituting in. So most of you at least did the front two. Didn't bother showing me too much of the others, but at least got the front two. I hear chuckles. Okay, cancellations. These are basically what we did when we found your point in discontinuities. We factored and reduced. Now here's the problem. I cannot substitute an x of 0 in here. It's giving me a 0 denominator. But when I graph this thing, it looks like it should have covered the 0 if I graph it. So if I can eliminate that by factoring and canceling out that factor, you can't cancel terms, but you can take out a factor. I now have a place where I can put my 0 in here and get what that limit would be, if in fact I could fill it in. Now remember on the graph, and it's always good to look at a graph graphically. Whoops, hold this here. It's good to look at it graphically because the graph makes you understand it a little bit better. So if we graph this guy, let me just put the graph in. Okay, so let's graph this and see what this looks like. Now it looks like there is a value for 0 in there. And if I again looked at my table, I would see the error. If I narrowed it down and I looked about this, eventually I'll find it. You see it come to the same point? It's approaching 1 from either side. So we looked at them graphically the first day, and then Friday we looked at them algebraically. If we eliminate that denominator, we can plug your 0 in and get a value of what y would be. And we did this when we did rational functions, when we factored it out. Remember keeping this little factor, and I made you say, point of discontinuity. And then we found that value, and then we plugged it back into what was remaining. Now, these have no problems. You could plug it into the original, you could plug it into the one we just eliminated. They have no problems. They plug right in. Those values we should be able to see on your table. If we wanted to look at your table and see them, we can find them on your table. I'm so frustrated here with this thing. Okay, so if we looked at your table and we looked for -1 and -2, we would find those. They exist. That limit exists. It's there. That limit is its y value. That's all we're finding. Okay. The next part works the same exact way. Again, you can't plug a 1 in there because the 1 would give you a 0 in the denominator. So if we factor and we reduce this out of here, this becomes what we used to say, there's your point of discontinuity. When x is 1, and then we would plug it back into this. So this gives me x is 1, y is 2. This is my point that would exist if I could fill it in. So all we're asking now is, what is the limit as x approaches 1? All it is your y value. So the limit as x approaches 1 is 2. Is the value of your function. That it would be if I could remove it. If it jumps, I can't remove it. If it's without bounds, I can't remove it. But this little guy, I can remove. These have no restrictions. Substitute them in. Am I taking it that this is good? Okay. We've seen these before. Like I said, this unit, we're just renaming these to be your calculus terms. We're talking limits now. What is it approaching? It could be there or it could almost be there. So we factor and reduce. So x minus 7, if we set that equal to 0, when 7 is there, it says it doesn't work, but it approaches the same number from both sides. So if we take it to reduced form and we plug in a 7, we can see what the y value would be. Therefore, that's the limit of this function as x approaches 7. Did I give you 15? No. Okay. Now, 17, yes, this looks a little strange, and we're going to rationalize. And it's really not that bad to rationalize, because when you rationalize and you multiply one radical times itself, it just comes out. We're using conjugates, so they're the perfect squares. It's not going to have any middle terms. So the middle term is going to disappear. It's going to cancel out. And then we're going to multiply the first radicals, first terms, last terms. You should be able to combine these and get rid of that. Your goal is slide this over. You want to eliminate this. So now we can eliminate the y. Once we eliminate the y, we can find the value of this function as y approaches 0. The value would be 1 over 2 radical 3, and graphically, it is still the same. It's just that in the decimal, it looks like that. Yes?
Wait, why do you have square root of 3 plus y plus square root of 3 over square root of 3?
You had to take this conjugate and multiply the top and the bottom by its conjugate. The only way to eliminate this y is to factor it out of here. So we've got to get these radicals away. So normally we rationalize the denominator. This time around we just have to rationalize wherever your radicals are, which is your numerator. Our goal is to try to factor out that y. Because that y says I can plug a 0 in there. But the only way to get that out of there is if I can factor something out of the numerator. Right now they're stuck in radicals. So if I use the conjugate, and the conjugate says multiply top and bottom by its conjugate, now it's freed it up. And I got them out of the radicals, and I was able to reduce the y. Did I give you 19?
It's number 10.
Number 10? Okay. Again,
We didn't have to do it.
you didn't have to do it. Right? I know these are numbered wrong. I don't know what happened to my other sheet. This guy is a complex fraction. The easiest way, put them all over 1. Find me your common denominator. Put your common denominator on the top of each term. Out comes this guy. You get a 1. Minus, watch the parentheses here. Over, and don't distribute. Leave this. If you distribute, you're never going to be able to eliminate the x. So distribute this negative sign. Out comes the 1s. And now can we eliminate this factor of x? So it's negative 1 over x plus 1. And when you plug the 0 in now, it'll be negative 1 over 1, which will be negative 1. And again, graphically, if you graphed it, you could see where it approaches. It's a point of discontinuity. My graph is not continuous at that point. But the limit as x approaches 0 will be that y value that it would be if I could fill that point in. We gave you this one?
No, it's like an absolute value.
No? Okay, next one is the absolute value. Okay. Now this one, solve this graphically. There's nothing to eliminate here. So as x approaches 3, I have a problem. 3 is not going to work. But I can't algebraically eliminate anything. So I go to my graph, and I notice this is why I can't eliminate anything. They don't come to the same point. This is a jump discontinuity. This is a discontinuity that I cannot fill in. So there is no limit. The limit does not exist when x approaches 3. From one end, it approaches it as y is 1. From the other end, it approaches as y is negative 1, but it will never come together. When you have lines like that at the step, that will never come together. The limit does not exist when x approaches 3. Okay, and the last one is a piecewise. Now, the only one you're concerned about is where the two pieces come together, which is at 2. Both of them use 2. One is open, one is closed. That's what I care about. If the open and the closed come to the same point, then that makes my graph continuous, because one will overlap the other. If they don't come to the same point, I'll be a jump. And if I look at 2 for both of them, they both come to the same point. They both come to the 1. So my limit as x approaches 2 is equal to 1, my y value. If you want to make 2 tables and do that, that's fine too. Get 2 lines. They just happen to hook up right when x is 1, up 2, and y is 1. Questions? There's no questions on these. We're talking about x approaching infinity from either end, either the positive infinity or the negative infinity. Now, what I want to look at basically is a horizontal asymptote. These 3 rules, if you remember back, are the same rules that we use for your horizontal asymptote. We're just renaming them to be a limit as x approaches infinity. That's why I said we did a lot of this work already. We're just kind of recategorizing them. So when we get here, you'll kind of see what I'm talking about. We had 3 rules. I'm going to graph this guy for a minute, this first one, so that we can see what this looks like, and then you'll kind of remember this a little bit, hopefully. All right, so we're going to graph the first guy. Now, notice that you have vertical asymptotes. You have vertical asymptotes here at the x is equal to negative 1, here at the x is equal to positive 1. When we factor this, first thing we tried to do was reduce this. Think back when we did rational functions. We tried to reduce it, we couldn't reduce it. So therefore there was no point of discontinuity. Then we said all the factors in the denominator were vertical asymptotes. So 1 minus x is equal to 0, and 1 plus x is equal to 0. So here's your vertical asymptotes. X minus 1, x plus 1. It's going to guide the end behavior of this little function. It's a rational function, and some things in the denominator don't work. These were our domain restrictions. If we could remove them, we had a point of discontinuity. If not, they became an asymptote. Then we said, okay, we also have 3 horizontal asymptote rules. And they are, if the degree in the numerator is less than the degree in the denominator, which the highest degree, 1 over 2, then you have an asymptote of y equals 0. This was your horizontal asymptote. Here's my horizontal asymptote. Look what it does. It guides this line. It will never cross my, it can jump a horizontal, but in this case it's using this as a guide. Now, as we graph this, here's my horizontal asymptote right here. On that axis, it's on that axis. My graph is going along this path. Okay? So as x approaches infinity, it will never, never, never hit the y equals 0. It will get smaller, smaller. It will approach y equals 0. It will approach our horizontal asymptote. That's the thing that's guiding its end behavior. And if you remember back, we always talked about end behavior. This guy is guiding towards the y equals 0. So when we now call this a limit as x approaches infinity, whether it approaches infinity from the positive or from the negative, we just say equals 0. We just give the y value. It's the y asymptote. That's all it is. But now we just call it equals 0. It will approach the y of 0, won't it? But it will never, never touch it. If I was to look in my table and I was to get as far down as possible, if I'm going down here, look how small these numbers are getting in my y's. They're getting small. They're coming up to the 0, but look, they're never, never, never going to touch it. See it? Real small, but never, never touch it. It uses it as its end behavior. So as x approaches infinity, I can make as many x's as I want on the positive or the negative in this case. The y is going to approach 0. So we, instead of saying our horizontal asymptote is y equals 0, we say our limit as x approaches 0 is 0. Okay, that was one condition. We had another condition. When the degree in the numerator is the same as the degree in the denominator, they're both a 2. We made a ratio. We did this. We made a ratio in here. So now I have a y is less than negative 2/3. I'm sorry, is equal to negative 2/3. Now, this line is here to guide the end behavior. Therefore, what we have to say now, as x approaches infinity, from the negative or the positive, it's going to approach that y value. See if we can put this in. Sometimes it's so much nicer to look at the graph. Fraction key. I like the fraction key on this because I have such a hard time getting half of these keys out here. Okay, so let's graph this. There's your function. See it? It's riding right along this, this y is equal to negative 2/3. It's guiding my end behavior. My y is going to approach that, but never, never touch it. So therefore, the limit as x approaches infinity, or as x approaches negative infinity, is equal to negative 2/3. It's equal to its y value. It will never touch that, but it will get real close to it. It will approach it. We also had another one. We had when the numerator is larger than the denominator, we had no horizontal asymptote. Do you remember what we used to look for when the degree in the numerator was 1 more than the degree in the denominator? What other kind of asymptote we used to look for? Slant. We looked for a slant. Remember? That was a slant. Usually it something kind of went like this, and we looked for a slant asymptote. Because when we graph this, these will have no bounds at all between them. So the limit does not exist.
Because there's no asymptote?
Because there's no horizontal asymptote, and when we graph this, you'll kind of see that there's no way that they can ever come together here. It's not going to approach a certain y value. So here. Oh, I should have kept the same thing. Do you remember doing these? So here's where it's going. It has a slant asymptote, but it doesn't have a horizontal asymptote. It's not going to approach any particular y. One's going out here, one's going out here. They're not approaching a y. But if we did a slant asymptote, you'd see the slant come through. And we did synthetic division. So in your review, that's in there. What usually happens is, once everybody starts doing your review, you start to remember these guys. And then you say, oh yeah, I remember them now. Now, in a case like this, remember what we had to do? We had to find a common denominator. So our common denominator was x squared. So we had to say 4x squared minus 3 over x squared. Now, you can use your rule. So when they're the same, we make a ratio. Your y asymptote would be equal to 4 over 1. And your limit as x approaches 0 is just the value of that y. I'm sorry, as x approaches infinity. It's just the value of that y. That's all it is. So it is the same exact rules that we use for horizontal asymptotes, because now instead of having an asymptote that it'll never touch but come real close to, that's the concept of a limit. It will never touch it, but it will approach it. As it approaches, what would that value be? That would be the value of your y asymptote. Does that part make sense? I always felt that part made a little bit more sense than the other parts.